So this is problem 4.1 in Elemental Programming Python textbook. So problem 4.1, and it's called computing the parity of a word. So what is parity? So parity is it's a concept, it's a key term that defines if a word have a parity of 1 or parity of 0. So like for example, if we have a number, let's say 4, so 4 in binary, we can represent this as 0, 1, 0, 0. So since 4 represent as 0, 1, 0 in binary, this have a parity of 1. I think some people call it odd parity. However, if we have something like 3, so if we write 3, we will get 0, 0, 1, 1. So this would be parity of 0 or even. The parity of binary word is 1 if the number of 1 in the word is odd, otherwise it is 0. Let's see. And the question asks us, how would you compute the parity of a very large number of 64-bit words? Compute 64-bit. I'll compute a single 64-bit. How to compute a single 64-bit word parity. 64-bit. It's a big number. So my idea is to break that 64-bit into like smaller chunk. So 64-bit, it's basically admin that have x1, x2, x3, x4, blah blah blah, and then we have x61, x62, x63, x64, like this. And so x is a bit, x1 is the first bit from the left, x2 is the second bit from the left. This is like most significant bit, and this is like a really significant bit. And how many chunk of 4 bits do we have? So this is 4, and this is also 4. 4 times, okay, let's do math. 64 divided by 4, we get 1, we got 2, and then 7, no, 6, 16. So we have like 16 of this, so this would be the first one, this would be the 16th. And like if we want to do this in a brute force way, we could just like loop. We can basically just like traverse through like each bit 64 times in order like to get how many ones are there. If there are like an even amount of ones, it would be a even parity. If there is an odd number of one, it's going to be a odd parity. But the idea is instead of looking each bit by bit, we can like create a lookup table. So in our lookup table, we can design a lookup table that represent the value of 4 bits. So basically you can do 0. So 4 bits, it can represent up until 0, 1, 2, 3, 4, 5, 6, 7, 8. So for 4 bit, you can represent from 0 to 2 to the power of 4 minus 1, which is 15. Yeah. So yeah, we have a lookup table that's saying that so for example 0 would be 0 would be 0, 1 would be 1, and 0. So for this one would be, so this would be this one as well, and 0, 0, 1, 1 would be zero, because like this is an even parity, so even parity we want to map it to a 0, and then we have 4, we'll map it to 1 because it's odd parity, so we map it until we get 1, 1, 1, which is 0. So when we have like this structure, this like lookup table, we can always traverse through to each chunk of the number and check if they are even or odd. And what we can do is, how would we grab this information? That's like a question. So in order to grab like this information, let's think something small. Let's think about a 8-bit number. So if we have a 8-bit number, we would have let's represent 8-bit numbers. Since it's 101 and 1001. All right, so this is an 8-bit number. So let's say that we want to grab the first 4 digits. The first 4 insignificant digits, 1001. How would we get it? let's call this number x. We need some sort of masking. So basically we want to AND this line with something like this. So if we AND this, you guys will get so this one AND with 0 is just 0, 0, 0, and this one AND with 1 you get 1, 0 AND with 1 you get 0, 0 AND with 1 you get 0 and 1. And then like with this information you can like go and look it up in the dictionary right here. And all right, so how did we get this portion? Now our question is to this part. How did we get this? So this is not 2 to the power. This is 8. So if we we kind of recognize that if we look at this portion, the difference between 1, 0, 0, 0, 0 and 0, 1, 1, 1 is that this is 1 less than this. So in order to get this, what you can do is, and we know that this, it's basically 2 to the power of 0, 1, 2, 3, 4 to the power of 4 minus 1. So in order to get this, it's basically 2 to the power of 4 minus 1. Right? Yeah. So we need to loop through the we need to loop through the number 16 times, which is better than 64 times. So what we can do is we can call x, and then x, we can call it 10, and then we do x and with can do and with x. I want to put parentheses to make it clear. Yeah. And what else? So x is this portion, and we want to create this. And in order to create this, we need to do let's call power. So in Python, there's a function called power, or you can do the classic way. You can do 2 and then 2 multiplication, which is power, and then you want power to an I, and then we want to minus 1. Let's make this like let's clarify this syntax. So we should have this. So basically we need to calculate 2 to the power of I first, and then minus 1 later, and then we can add it in this. Yeah, that's about it. And in order to generate I, it's basically just a for loop. So that would just be for I in range of So we want to start with 4, and then our increment is 4, and then we want to finish at 64. However, Python range is inclusive, so we have to, if we want 64, if we want our last I to be 64, we need to write 65. But is this always true though? Let's think about it. Not quite. Not quite. There's some error in here. Let me give you another example. So an example of what if we want like just this portion instead? Yes. If we want this portion, we need to let's do okay. So if it's just want that portion, we need to end this with I mean, we can always add everything with this number, which one we had already, but it will get us 1101, and this would be all 1001. But the idea is we want to shift everything by 4. And we want to shift everything by 4 to the right. How about the case that we have a 12 bits instead? So if we have 12 bit instead, will this idea still be hold? So the idea is just like we eliminate everything on the front and then we shift. Yeah, I think it will still be whole. So in the case we just end everything. So we will get 1 0 0 1 1 0 1 1 1. Yeah, then we just shift 8 10. So first we shift 0 4 8. Yeah. Yeah, so right here, I think all we need to do is like shift to the right by I minus 4. So the first iteration, it won't shift at all because our first I is 4. So 4 minus 4 is 0, so it doesn't shift. Yeah, like this is the main picture. Let me think about other edge cases. So like, let's erase everything. So let's say like this is the number that we have. Right? But our equation is like 64-bit. It's just like for scaling up. But it's going to be the same when we have like 12 bits like here. So for the first iterations, we just need to grab this. So in order to grab that, we need to do the whole thing, which is x, and then we AND it. So we do AND, and then we do 2 to the power of I, but since our I, the first I is 4, so 2 to the power of 4 is 1, 0, 0, 0, 0, 0, 0, but with minus 1, so we'll get we will get all 1 right here. Oh, it's like this. Oh, 2 to the power of 4 is like this. And then we will get and then we minus, so 2 to the power of 4 is 1, 0, 0, 0 with 4, 0, and minus 1 will give us this. And then we AND it with x. Since we AND it with x, we will, so this all, we have all 0 in front of here. So we will get just 0. And then we shift 4 minus 4, which is 0. So we don't shift anything at all. So we just get this, and we look it up in the lookup table. We see that 0, 0, 1, 0 is a odd. It's an odd parity, so we can like record it. So let me like write the code. We write it right here. So let's call that function. This is that. Call it solution, and it take a num 32-bit, right? So first we want to create this dictionary. So we call lookup table. So lookup table is basically like this table. So in Python, the way that you can import it would be, so like 0, 0 here would be, you can do lookup table, then you do 0 is equal to 0, and we have to do that 16 times. But the good thing that when we have lookup table, we use a little bit of memory. However, we save us a lot of time to compute, to figure out like the solution. Like instead of looking at the bit 64 time, we only look at the bit 16 time only, because we have only 16 chunks of this. So we have to do this like, we have to hard code this 16 time. So for example, look up table of the last number, which is let me think, 15. Have to be 0 as well. But we have to do this how many? 14 more times right here. 14 more. And then we can write our for loop. So we have for. So as I mentioned earlier, we want to loop through this 16 times. So, and our first number is 4, and our last number is 64. And each increment is 4, so we go by 4, 8, 12, 16. So we do for I in range, basically just copy that for 465. Everything. Let's also like create another variable like on top somewhere here. It's called count. It's equal 0. So right here, we want to traverse through this number like 32 times. So what we want to do is, we want to do, let's call that variable is 10. 10 is equal to, so I'm going to rewrite what I just erased. So it's basically just 10 num 32, and you want to end this with a num 32. No, you don't want. You want to end this with 2 to the power of I minus 1, and then you want to shift it to the right by I minus 4. So you count and start with 0. So initially, let's say that if the number is like 0, if the number is 0, it would be an even parity. So it starts with even parity. However, it needs to calculate, you need to compute the new parity of each chunk. So we just do XOR. So if we have, so in the case that we have, let's say that in the case that we have a chunk that is even parity and another chunk that is like odd parity, we would get odd parity. However, if like there's two chunks like odd parity, we will get an even parity. So there, like in computer science, there is a logical expression called XOR that allows us to do that. So that is called XOR. So what you want to do, you want to count, and then you do, like in Python, XOR is this sign. Then you do 10. So after that, you will return count. So count will either return 0 or 1. And 0 would be even parity, 1 would be odd parity. Yeah, that's about it. Let's analyze this time complexity. So for time complexity, this for loop have to run 16 times, because This for loop will generate 16 times, because this for loop will have to go, we will generate this number 4, 8, 12, 16 until 64. So there is a 4 value incremental, like from one number to another number. That's why it's only 16. That's why it saved us like it saved us about 64 divided by 16 times, which is, let's see, which is 4, I believe. 4 times 6 is 24. Yeah, so we save about 4 times. So instead of like traversing through the bit 64 times, we only traverse 16 times. But the flip side is we use some memory right here. So our lookup table is not count. Our lookup table have to be O of the 16, because it's a constant, because we need to save like all this value right here. So it's O 16, and time complexity, since it go through like the loop 16 times, so it have to be O 16 as well. Yeah, and this is for the O1. Yeah, so it's all depending on the type of system that we running on. So if the system is not limited with the memory, we can use this approach to speed up our our algorithm a little bit. However, if our system doesn't have like a lot of memory, for example, the system that, especially like embedded system that doesn't have like much memory, we're probably better off use just like traversing to like 64 times. But this is like a different perspective on looking how we could approach by using like a lookup table to help us to save some time. All right, thanks.